All right. So let me take it away first by showing my gratitude. Stats Clinic is something that I've always wanted to do. And when Ibrahim said to me, "Hey, would you like to do this?" I was like, "Would I? Of course I would." And I'd like to introduce myself to you all first, and then I'll tell you how this class is going to go. My name is Aboa, and I'm a public health and health outcomes researcher. And I approach public health from how public health, I believe, is supposed to be approached. It's not an academic science. It's not an ivory tower science. It's an on the streets kind of science. Public health is the kind of thing that you use to run your personal relationships, your interpersonal relationships, community level, societal, political level. And I'm going to try to bring some of that to you as we talk today. Yeah, and moving on to how this class will go. My preferred style is a cold call method. And when we cold call, it's not because I want you to have the answer. In fact, you're encouraged not to have the answer. If you get to know me, you'll find out that I'm constantly talking over people. So I don't want you to have the answer, but I want you to respond to some questions that I'm going to ask. At this point, I'm going to say that I cannot see anyone, so maybe the cold call may not work. But feel free, if I ask a question, feel free to unmute yourself and then jump in. I'm not going to wait for people to respond. So jump in and jump out as you can. Today, we're going to be talking about epidemiologic measures. So let me start, true to what I'm saying, let me start by asking a question. If I have 20 Naira and someone else in the audience has 10 Naira, can someone tell me what's two ways we can compare me and that person? Okay, no response. So here's what it does. Here's what you do. Research is about comparisons, right? And when people talk about measures of association, they really are talking about comparing two groups. So in the question I just asked you, if one group, let's say the Nigerian group, has an average of 10 Naira in their bank accounts, and a Sierra Leonean group has an average of $20 in their bank account, there's only two ways you can compare those people. You can either subtract or you can divide. So you can say Sierra Leoneans have 10 Naira more than Nigerians, or you can say Sierra Leoneans are twice as rich as Nigerians. If you put that in your head, then you've understood the basis of all research everywhere in the world. So people say vaccine efficacy is 92%. What does that mean? It just means that if you compare the vaccinated group to the group that's not vaccinated, there is an increase in disease prevention of up to 92%. That's vaccine efficacy, and we're talking in terms of COVID. So you see how I'm bringing what we're learning away from the academics into conversations that we're having every day. Okay, let's move on. So this is a really nice picture of a fishing boat. Let's jump right into another concept. By the way, Ibrahim, is my picture on the screen blocking the slide, or can everyone see just the slide? Dr. Abioye, help me here. Okay, you're muted, just in case. Yes.
Okay, sorry, I stepped away for a moment. Yeah.
Okay, can you see the entire screen, or can you see my picture?
I can see both the entire screen and your picture on the
so
slide.
let me move my picture up, and let me move my picture up, and okay, great. Oh, someone said we can see both. Okay, now I can see. I'm using two screens, so I'm going to look from side to side and look at what people are saying as I scroll down. All right, let's go. Okay, so let's talk about prevalence. On Twitter, some days ago, I pointed out to someone that prevalence is a proportion, you know, and some people might say, oh, maybe not, maybe, okay. But here, one of the measures that we constantly use in public health is a prevalence measure. And what a prevalence measure helps you to do is helps you understand the scope of the disease, the scope of the disease or the scope of the problem. So a prevalence really is just the proportion of people out of the total proportion of people in a city, in a country, or in a certain population who have the disease of interest. So let me give you an example. Some people are going to say, if you, for example, were the Minister of Health and you wanted to treat either lung cancer or diarrhea, what you would do is you would look through your records and say, of all the patients who come to our hospitals or in our community survey, of all the patients who come, what proportion of them have lung cancer? You say maybe 10%. Of all the people who come to our hospitals, what proportion need treatments for diarrhea? Well, 90%. It becomes easy for you to say, okay, let us treat diarrhea and over lung cancer. Let us prioritize diarrhea over lung cancer. That's the importance of prevalence. There are other decision-making tools, of course. Diarrhea may not kill everybody that it affects, but cancer may kill everybody that it affects. So you bring in that multi-level criteria decision analysis. So prevalence is not the only thing you use. However, a prevalence is important because it describes the scope. And so how do we calculate prevalence? As I said, you take the number of people that you are concerned about, the number of people with cancer, and you divide that by the total number of people at risk, or the total number in the study population. It's the latter, actually. And the reason why this definition is important is when we move, for example, to cumulative incidence, you're going to see that there's a difference. Now, what is cumulative incidence? So we start with prevalence as the crude way of defining a problem. Or 20% of children that are born in this hospital get neonatal jaundice. Wow, okay. So 20, that's a huge number. But when you need to drill down, you're going to think about, okay, let's look at a disease like cancer. When you come into a city, let's say, and cancer is a bad example, but let's use it. Let's say that there are 15% of the people there are living with cancer. They're already 15%. But now you as the minister, someone has told you that it looks like it's not only the burden of disease, the prevalence, but there is a trend. There's an increasing trend of cancer in people, in people in our city. So you come in and say, let's calculate the cumulative incidence. It means that you take away the people who already have this disease, and then you start counting the new cases. And then you divide that number by the total population at risk of the disease. So remember that in earlier, you can see here, it says total number of individuals in study population. But in this case, you do two things. The cumulative incidence is a specialized form of a prevalence, if you allow me to say that. You take the new cases that happen and you divide them by the total number of people at risk. This total number of people at risk means that the people who had cancer when you came into that community, you remove them from the denominator. So for example, if there are 30 cases of cancer in your community and there are 100 people in that community, and over a period of 1 year, you have 10 new cases, your cumulative incidence will be the 10 new cases divided by 70. You're going to remove those 30 people that had the disease. And what cumulative incidence helps you understand is what is going on over time in the community. You want to take out people who are already old and already have the disease prevalent. So you see that there are different levels of decision making. You say, oh, this is a global burden. But now this is the trend that we are seeing. 20 cases would develop every year in this our community if we don't do something. Remember, public health is for decision making. Research is for decision making. Public health and public health research are not academic things. They are things that you should be applying to your lives, to your company, wherever you live. And this is a serious takeaway that I want you to consider. Okay, so here on this slide, what we have really is there are different patterns of cumulative incidence. So let's focus on this. Let's focus on this thing about late incidence. And what we're trying to bring here is time. Time is the most misunderstood concept. I'm not going to wax philosophical, but time is time is something else. So think about this, right? If you were measuring the incidence of dementia in Nigeria, it's going to be so small that you're going to say, oh, we don't need to prioritize it. And maybe you'll be correct. But if you know about Nigerian vital statistics and demographics, you know that only 5% of our population is over 60 years old. And so given that that is the case, you are not going to see a lot of people with dementia. However, if you start to look at people who are beyond 80, you would begin to see more and more cases, or quicker and quicker cases, as people turn 80. So when you're thinking about these measures, you have to take into consideration over what time period are we looking at? And is our time period appropriate for the population we are looking at? And you can see, I don't know if it's apparent to you, that what I'm doing is giving you the different tools with which you make your decisions as public health researchers. So you don't go with whims, you don't go with fads, you don't go with people's opinions, you don't go with who's the popular person in the group telling you stuff. You can have objective criteria to say, should we focus on HIV versus should we focus on malaria in Africa? Should we focus on dementia or should we focus on diarrhea, etc., etc.? Okay, so there are issues with cumulative incidence, just as there are issues with prevalence. There's this, look at this wonderful example, right? Everybody eventually dies. Elon Musk has not solved that problem yet. So if you follow people for a really long time, everybody will eventually have the outcome, especially if that outcome is death. So again, time comes into consideration when you're thinking about cumulative incidence. So again, this is a decision-making thing. If you're doing a study, you say, at what time period should we start, but at what time period should we cut off our study so that we are not falling into this bias where every cumulative incidence falls falls under one. There's also the issue of time varying exposures. And Ibrahim and I were discussing this yesterday. So the problem with cumulative incidence and prevalence, sometimes it is not sometimes, it's like you count each individual as one. However, individuals may have repeating results. For example, here you can see that hemoglobin is measured several times during a woman's pregnancy or during a person's pregnancy. And so if you want to ask what is the incidence of anemia, if one woman was anemic in first trimester and anemic in third trimester, do you count it as one or do you count it as two? Those have implications. And there are also some issues like loss to follow up. Some people would leave that city and you may not have information about them. But I believe we'll talk about that as we go on. I'm not sure how I'm doing with time, so I might speed things up, I might take things slow. Please feel free to tell me if you need me to take it slow. I'm looking at the charts on my left. Okay, let's talk about the most difficult of all these three. So we've talked about prevalence, incidence, cumulative incidence. Let's talk about incidence density. This is a really good, let's call it the gold standard for doing research. Now, here's the issue. When people come into a study, they come in at different times and they leave at different times. So if you wanted to know, for example, how many children in Ikeja or Freetown or Monrovia get diarrhea in the first 6 months, or in the first year, in the first 5 years of life. Yeah, let's use a long time period. And maybe 15% of the children in Monrovia, their parents have to move out of Monrovia for whatever reason. So you see that for those children, you're not going to have a 5-year time frame. You're only going to have, if they move out in the second year, you're going to have only 2 years for those people. And you have to take that into consideration, because let's say that child did not have diarrhea in the first 2 years. How do you know the child did not have diarrhea in the third year after they left? So what an incidence density does is take that into consideration and make sure that we are only counting the time people spend in a study instead of the people. So let's look at this example here. You can see that person A spent 1 year in the study before they died. Person B spent only 6 months, and person C spent 1 year. So instead of saying that the total number of participants is 3 people, you use the time each participant. So you're going to say person A spent 1 year, so that's 1. Person B spent 6 months, so that's 0.5 years. And person 3 spent 1 year, so that's 1. So you're going to say these people, the denominator is person years, not 3 people, 3 person years, because it's 3 people, it's 2.5 person years, 1 year, 0.5, 2.5 person years. It's true that it's 3 people that contributed that, but these 3 people only contributed 2.5 person years. So when they ask you what is the incidence rate of death in this population, you look at the total number of deaths, which is 1, divided by the total amount of person years, which is 2.5. So you can see here that the incidence rate is 1 death per 2.5 person years, or 0.4 deaths per person year. This helps you solve the problem with loss to follow-up when people leave the study early or when people join the study late. Okay. So here's another example, and I really like this, and I'm happy that it's here. You can see a lot of people in this study, and you can see that A and B joined at the beginning, but C and D joined at a year later, and K and L joined like 5 years later. So how do you do this if there are people joining and leaving at different times? You use the person years. So here you can see how many years each person's contributed to the study. And so you see the total is 107.7 person years, whereas, and the number of events is 3. And so you can see that it is 3 divided by 107.7. I don't know if there's anyone who has questions. Hey, please feel free to ask. I think there's another question chat, but I'm happy to. Oh, so I see a question. So the person years used for the calculation is the summation of the total number each participant spends in the study. Absolutely, that is correct. In fact, that is so correct. Maxwell, you should be teaching this class next year. Okay, so we're going to skip this.
We have a question.
Oh, please.
Sorry, I think there are two people who are raising their hands.
Please, fire on. Can you help me ask their
Osho,
questions?
Akim.
Okay, yes.
Sorry, go ahead.
Question is that there's a difference in what the lecturer said concerning the total number of person years in the slide given to us to the one he is using now. In the one given to us, there's 1.5 person that is in the slide, but the one is using, there's 2.5. It is 2.5 person that is there.
Okay, so that's an error, right? I was looking at these slides yesterday and I thought to make changes. So okay. I believe this is more correct. Dr. Abiyo, you feel free to look at this and let us know if there's any disagreement.
Yeah, I think you're right. Yeah, 2.5%.
Okay, so just in case there is some confusion, let's do this together. So you see that this person A spends 1 year, then dies, right? So he dies at the end of 1 year. So that's 1 year. Person B leaves the study. You see, this, whatever sign this is participant dropout. So this person is 0.5. So that's 1.5. Whereas person C stays the entire thing and does not die, thankfully. So that's another 1 year. So in total, we have 2.5. And there's only one event. So this is the more correct of both slides. And thank you so much for yeah, thank you so much. Oh, did I give my shout out to Maxwell? I really like the way you put your question. Your question is actually the answer. So good job. What if it's in months? Zainab asks. Exactly. So it becomes person month. So in this case, what we would have is 12 plus 6 plus 12, which is 24 plus 6, that's 30. So the answer becomes 30 person months. What if it's in days? It becomes person days. What if it's in hours? It becomes person hours. It depends on what you want to do with your study. Confuse everybody or convince everybody. That's the way to do research. And that's not a joke. That's really what happens. And you can check out the book, How to Lie with Statistics, or you can watch Dope Sick on Hulu. It will show you how people lie with statistics. Is there any other question?
Anthony has a question.
Anthony, hit me.
Yes, thank you very much. Where I had a confusion, you just explained more, especially with the drop off.
Okay.
So I understood it now.
Okay.
I got a 2.5.
Okay,
thank you very much.
Sweet. You're welcome, sir. Okay, so let's move on. And
we have one more question. Sorry.
Okay, let's do it.
Joshua has a question.
Okay.
Thank you very much. Sorry, just go back to the last slide. I just had a question about
this one.
No, the one with the. Go back one more. Yeah, this one. So
okay.
Here you're doing. No, go back. Sorry, the forward one more.
Forward.
This one, yes.
Okay.
So I'm just trying to think about the context and the relevance of all the candidates. So some people drop out, some people drop out, some people stay through the course, but then so why? At what point do you basically factor in the duration that's applicable that you use for your explanation, if I may use the word?
Right. I think I like that question. That's a really, really good question, right? So for instance, you are saying here that why should we, okay, let's look at person J. I think what your question is asking is, why should we consider person J in this study? He came into the study and maybe the next day he left. What's the point of putting him in the study? And the question is, if you look at person F, so this person spent the same number of time, 3, right, and got the outcome. So it's possible that he could have come in, maybe this person J could have come in, and the day immediately after he came in, he got the outcome. So we cannot say that, oh, because he spent too little time, we should throw him out, right? That's one answer. But you are right. There may be there may be enough, depending on what we're talking about. And pardon me, I'm scratching my nose. I have crazy allergies. But there may be, it depends on the disease you are looking at. It may be possible that you say, if a person does not spend as much as the incubation period, then we'll throw that person out of the study. So it's really context specific. We cannot know. For example, if we know, if someone receives a vaccine and we know that oh yes, this is not, for example, I saw this study. So if you receive the COVID vaccine, your immunity kicks in 2 weeks later. So if a person drops out of the study before 2 weeks, you can assume that this person is not an eligible population for your study, because you want to look at, your population for your study is not just people who have received the vaccine, but people who have received the vaccine and have had the effects of the vaccine activated. So again, it's very context dependent. So both situations may be correct. I hope I've answered your question. Okay, great.
Thank you very much.
Super. So how am I doing with time? Is there?
I think you're doing okay.
Okay.
Yeah.
Okay. Did you want to say
before
something?
you move forward, I think Amina has a question, but I'm trying to answer it in the chat. But I think I need more clarification. Do you want to answer it? Ask it live, Amina. I'm going to let her talk.
Sure.
Sorry.
Concerning the slide, it's for incidence ratio. I just wanted to know that where do we get like 0 points, because we had this workshop, like I'm just understanding this person here kind of thing. But where do we get fine 0 point something? Like where is the 100 or 1,000 coming from?
Oh, good question. So this is something we take for granted, right? Okay, so remember that public health is for decision making. So Dr. Abioye is an epidemiologist. So maybe he would not totally agree with me that public health is for decision making. Maybe you say public health is for epidemiologists to do science. Great. Okay, do your science. But for me, all research is for decision making. That's the school of thought I come from. Now, so if you go to the Minister of Health and you say, Minister, there are people that are dying, and it's 0.028 per person here, he'll just be looking at you. Okay, when you finish, you'll come and be going to your house, But if you tell this person that it is 28 people for every 1,000 hours that people live on Earth, or 28 people are dying for every 100 years that people live on Earth, given that 100 people in anywhere in the world in 1 year would accumulate 100 years, then he can begin to reason with you and say, oh, this makes sense. So if there's 100 people living for 1 year, 28 of them will die. Wow, that's a problem, And so that's why we multiply by 1,000. Right? And so we take it for granted, but here that's the exact reason. It is for decision making. Again, other people will disagree and say it's for the science. I don't know, but this is how this is the school of thought I come from. If it does not make sense to your grandmother, it does not make sense at all. Okay, so let also okay, I see Ibrahim answering questions. Thank you so much. Ibrahim is my big bros, so shout out to Ali. So let's talk about odds. And the reason why I want to talk about odds is because, sorry,
we have one more question.
Oh, okay, let's do it.
So coming. You have to unmute, sorry.
Okay.
Yeah.
Yeah. Thank you for the video. I would like to ask that the total number of years, that the cumulative, is it significant for those that came out with the disease during the study?
How do you mean, is it significant?
Like maybe, like for example, from this graph, B spent 11 years, spent 3 years,
okay,
and spent 6.2 years.
Mhm.
I'm talking about the cumulative. Is it significant in this study when you are trying to address for those, we are using per person. You told us you are not using per person, we are using the total number of years spent. So I'm now asking the cumulative for those that came out with the disease.
So if I understand you well, you're asking that, do we add these people's time into the denominator? Is that what you mean?
Exactly.
Yes, we add up to the time. So when you read these papers, people are going to say things like, we followed participants up to either when they got the event, when they left the study. So when they got the event is B, when they left the study is A, or until the end of the study is C. So when you're reading, the next time you're reading a paper, look out for that statement. We followed participants up to when the earliest of the three, when they got the outcome, when they left the study, or at study end.
All right.
Okay. So thank you for that question. I mentioned earlier that I really like this slide, and we can see how much comment and conversation is. Hi, please. What is represented on the x-axis? So it's not a real x. X is this one. So it's time, right? So this is like the years of the people. 81 years. It may not be very great on the x-axis, but really the x-axis is usually time. And so you look, maybe you are saying this is 1981, 1982, or 2083, 2084. So this is time. Okay, let's move to odds, because I really, really like odds, because it gives me a little bit of a brain tickle. And also we know that people are gambling a lot these days. There's a Mr. Bayo on Twitter, and it's making many people jump into this thing. So what really are an odds? We've talked about a proportion, and we say proportion is the number of people that have the issue of consent divided by the total number of people. But what is an odds? When you get to odds, you are looking at the likelihood that something would happen. So let's think about Manchester United playing yesterday. And someone says, Ronaldo will score a hat-trick. And someone will say, what's the odds of that happening? And that the answer of the definition, what that means is, what are the chances of this thing happening? What are the chances that a child would have diarrhea in the first 6 months? And forget about all these formulas here. There are things you need to know, but there are things that you don't need to know at the same time. The odds or the chances of a thing happening is the prevalence of that thing happening divided by the prevalence of it not happening. And now you see that here we're using proportion. And I mentioned earlier that I argued with people that the prevalence is a proportion. The prevalence really is a proportion. So let's talk about what are the odds of a random 6-month-old having diarrhea within the first year of life. And here's the answer. You take the prevalence of children who have had diarrhea, or you can't have prevalence. You know what? Let's just use the example. The prevalence of children who have had diarrhea in the first year of life. Let's say 30% of those children have diarrhea in the first year of life. You take that number, you divide it by the prevalence of the children who do not have diarrhea. And the prevalence of people who do not have diarrhea, if 30% had diarrhea, that means 70% did not have diarrhea. So your odds is 30 divided by 70. So if someone says, what are the odds that Ronaldo will score a hat-trick? You take the number of times he has scored a hat-trick in a match divided by the total number of times he has not scored a hat-trick. You divide those two numbers, and that's your odds. And then you become the new Mr. Bayo on Twitter. So this is a little different from a proportion. It's a little different from a proportion, because in a proportion, you divide by the total number. You say, if the number of children with diarrhea in a city is 30 and the total number is 100, your prevalence or your risk becomes 30 divided by 100. Your risk is 30 by 100. A child has a 30% chance of having diarrhea in the first year. But what are the odds that this child will have is 30 divided by 70. So be on the lookout where you use a risk and where you use an odds. Okay, let's keep going. Okay, so oops, shown you the answer already. So let's do this. And question for Dr. Abioye, is this on a poll, or is this do people just answer?
It'll be a Zoom poll. I would launch it now, and then they'll see it on their screen.
Okay, super.
You might want them to read it for a moment on here, and then before I launch. Yeah.
I'm going to pause. Okay. I say it's launched. When do we move on? When does the poll close?
Closing the poll now. So I'm then sharing the results.
Okay, so so 75% of people said the odds ratios of cancers in town X. Which of the following cannot be estimated? So I think that's the right answer. Oh wow, look at it. That's the right answer, 75%. So let me ask there's Tolulokwe Amuso. I saw your name. So Tolulokwe, can you tell us what the odds are that a person in this class will get the answer to this question?
Good evening. Thank you for giving me this opportunity to speak. You said the odds that a person in this class will get this question.
Correct, yes.
That would be the number of those that got it over the number of those that did not.
Okay, and what's your answer? It's the proportion, right? Not the number.
Sorry, yes. The proportion of that got it, yes.
So what's your proportion? 75% got it right.
So that would be 75% over 25%.
Which is?
3.
Exactly. You're the new Mr. Bayo in town. Let's go. Okay. Question 7. Let's launch the poll 7, and then we can discuss. If anyone does not understand why that's the answer or whatnot, feel free to let us know. Okay, Babatunde Amo answered, even though we asked Mr. Amuso or Dr. Amuso. So Babatunde, get ready to answer the next question. Thanks for volunteering. Okay. So once the poll is closed, I will continue talking. Otherwise, I will practice being quiet.
The poll, sharing results.
Okay. So we see 70% of people answered 50, and okay, so the answer is 50. So Mr. Amal, if that's your correct title, what's the odds of people answering 30 to this question instead of 50? And the answer, not the answer, but if I let you know that 18% of people selected 30 as the answer.
Okay. Good evening, everyone.
Good evening.
Sorry. The odds will be 0.22.
And how did you get that?
That will be 0.18 divided by 0.82.
Okay, great. So it's 18% divided by the complement of 18%. So just in case this, let's use this opportunity to introduce new vocabulary. When you have a number, a proportion in decimal point, and you subtract that number from 1, it's called the complement. You guys probably learned that in math, and maybe you forgot, maybe you didn't know, but yeah. Good. Thank you so much, Mr. Mo. Oops, shown the answer. Okay, let's run the third poll.
Sorry, before you move forward, I think people want you to talk about the odd calculation again.
Okay.
For a moment. Yeah.
Okay, great. So an odd is the likelihood that the probability, people say the probability, people say the proportion, they're used interchangeably. If a thing happens, the proportion of times it happens divided by the proportion of times it did not happen is the odds of that thing happening. So let us use an example. Let's see. I'm trying to find something that's not very complicated. Let's use should we use politics? Okay, let's use politics, right? What is the odds that the party currently in power will win the next presidential election? And the answer to that is when you look at the history of that community, that country, that society, how many times in all the elections has the party in power won their next election? Let's say it happens 50% or 60% of the time. The incumbent wins re-election 60% of the time. If you're now looking at a future election and there's an incumbent, someone will say the incumbent is not going to win. And you say, no, the odds are in favor of the incumbent because 60%, historically, 60% of the time, they have won. But that's not all. You have to divide that number by the complement of that number. And the complement of 60% is 40%, meaning you subtract 60 from 100 because percentages or proportions are bound between 0 and 1, between 0 and 100%. So the odds would be 60 divided by 40, which gives you an odds of 1.5. The higher your odds, the more likely a thing is to happen. So when someone says, oh, so-and-so will win, it's not just because you like that person. You don't say Chelsea will win because I'm a Chelsea fan. That's not very, that's not very scientific. You say the odds, and this is what betting houses use to draw you in. The odds of Chelsea winning is because they've won 80% in the past, and 80% divided by the complement of 80%, which is 20%, is 4. So there is a 4 times higher odds of Chelsea winning this match than the other person winning this match. That's how you calculate the odds. I hope I've not confused you by using a difficult example of politics. Shall we move on?
Yeah, somebody wants the answer to poll 6 I think it's the same one. That's the odds one, so we can move on. Yes.
Okay. So if you, is this the next question? Let's launch this one.
Yeah. Okay.
Okay. Let's do that. I'll read the questions and be quiet.
Closing the poll. Sharing results.
Okay, so here we have, this is really close. This the odds of so we're going to call Amina to the stage now, because she says she did not understand, but I'm sure that because I'm a genius at explaining things, I'm sure she understands now and can teach the class. So Amina, get ready to unmute yourself and let's discuss this odds thing one more. I told you it's a bit of a brain tickle, and that's why we're going over it. Poll 8, what is the cumulative incidence? So new cases, remember that your cumulative incidence is new cases divided by people at risk. If a person already has the disease, they are no longer at risk, except of course it's like an infectious disease like malaria that you can get in January and get in June and whatnot. So let's look at the answer to this. It's 30 per 980 people. So only 36% got it. That's 2 out of 5. That's about, what's 2 out of 5? That's about 1 in 2.5. Is that 2 out of 5? 1 in 2.5. Yes. Okay. So even me, my math is faulty sometimes. So more people voted, 42% voted that it was 30 per 1,000 person years. So remember, so I had this professor in accounting, and he was really funny. He used to say, and I'm not going to swear, but he used to swear. He would say, read the effing question. He would say, in accounting or in math, people get the wrong answer, not because they don't know the stuff, but because they don't read the question. So when people saw incidence, they assumed that it was incidence rate. But if you read the question carefully, what was cumulative incidence? And if you remember that in cumulative incidence, you don't use person time. Now, someone will say, how do I know? Tomorrow I might forget the difference between cumulative incidence and incidence rate. Here's the thing. A rate is time. If anyone says rate, they are talking about time. Incidence rates, they're talking about time. Rate ratio, they're talking about your incidence rate because there's time and the ratio of that. Interest rate. So if you say interest rate of 5%, right? I'm going to do what people call a shameless plug now, but hold on for it. When people talk about interest rates, they say interest rate of 5%. They say there's no time. No, it's the short form. What they really mean is 5% per annum, per year. So there's a time there. So anytime you hear rates, they're talking about time. So if you want to remember the difference between cumulative incidence and incidence rate, it's the one with the rates has to do with time. And that is why. So let me ask Amina. Amina, if you can unmute yourself. I don't know what you chose. Did you choose A, B, C, D, or E? I like the 2% of people who said, I don't know. That's a beautiful answer. And so Amina, which did you choose and why?
Okay. I chose D.
You chose D. Tell us why.
I think I didn't understand the question. Like I didn't read it well. Yes.
Okay. So you're one of the people that did not read the question. Okay. So let's imagine that the 18% of people. Oh, I mean, as you still have to unmute. Don't worry. Let's imagine that everyone who chose D, that's 18% of the people, chose D because they did not read the question. What are the odds that in a class like this, people will not read the question properly?
Okay, that will be 18.
Let's bring out my calculator for you.
Okay, 18 over 82.
All right, and that gives us 0.22. Right? Okay, last question, Amina, because you are on genius mode. What is the proportion or the prevalence of people who will not read the question when you ask a question like this?
That will be 18. Okay, the prevalence of people that will not read the question. Okay.
So a prevalence is a proportion, you see? So yeah, so
18 over 100 something.
Divided by?
18 divided by 100.
There you go, which is 0.18. So the odds will be higher than the prevalence. They are not the same thing. So if you want to gamble and someone says, let's use the prevalence, you say, no, let's use the odds, okay? Public health is for your personal life. So I've just given you a demonstration if you're into gambling. So let's take a 5-minute break in 1 minute. I told you guys I was going to do a shameless plug. Here's the shameless plug. People tend to borrow money and say, give me 100,000, I'll give you 120 in 2 weeks. That is a very horrible idea because remember that your interest rate is per annum. So 20% on 20,000 on 100,000 is 20%. But it is not 20% per annum. In 2 weeks, 2 weeks is 20 is what's 2 weeks out of 1 year is 2 over 54. So you are actually borrowing money at 20 times about 24, which is about 500%. Shameless plug, you should not do it. Okay, so this is 155. Let's take a break for 5 minutes now that you understand rates and how public health can be used for your personal lives. Okay, I'm going to stop my camera and pause myself and then see you guys in 5 minutes. Okay, okay, okay. How's everyone doing? I missed all of you. I missed you so much, and I am happy to be spending the remaining 1 hour with you. Okay. And while everyone's getting their cup of water or ice cream, um, let me recap in 1 minute what we've learned so far. And the first thing is that public health is useful for decision making, and public health is useful for it's not an academic science. It is a personal, interpersonal, organizational, community, societal, and political tool. So the things that you learn here should be applied in your daily lives. And I showed you an example of that using the epidemic of betting and gambling that's going on in different African countries. And if you're going to participate, you should have some, you should exercise some caution to understand what your odds are. We looked at prevalence, which we say is a proportion, and it looks at the number of people or with a situation of interest divided by the total population, and is expressed as a percentage, or is expressed between 0 and 1 as a decimal. We looked at cumulative incidence. It drills further down, and we're looking at the new cases divided by the people at risk. If a person is an old case, they cannot be at risk of the disease, except it's like an infectious disease that you can get again and again, like malaria. Then we looked at incidence rate, because in research, people don't join the studies at the same time, and some people leave the study at some point, and so we use people time. And so we use person time, person years, person months, person dates. The denominator becomes the number of hours, days, years, months that each person in the study contributed to the study. And someone asked the lovely question, do we add the time of the people who have the event? The answer is yes. And we add the time up until they get the event and not beyond that. So bear that in mind. Okay, 2 minutes. Someone said, can we explain? Oh, someone's asking if my voice can be amplified. Okay, get ready to hear me shouting. So I hope this is better. So can you explain poll 8? Yes, I can explain poll 8. Let's do that very quickly. And Adeniji Lasisi, you will be asked the question, because you ask a question, we'll ask you one. Just so that we have this as an interactive session. So we know that by December 2019, the last day of December 2019, there are people living with cancer. Once you have cancer, we are assuming that you cannot get a new cancer. That's not exactly true, but you know, prayers that if you have cancer, you don't get a new cancer. But let's imagine that you had that there are 20 people out of the town of 1,000 people who have cancer. In the new year 2020, you get 30 new cases. Your cumulative incidence, remember, it's new cases divided by the people at risk. By 2020, out of that 1,000, only 980 people are at risk, because 20 of them already have cancer, and we've assumed that they cannot get cancer again after having it in the past. So therefore, your cumulative incidence is new cases divided by your cases at risk, which is 980. So that's why you have 30 divided by 980. Okay, I hope that's the, oh, we have one more poll. Let's do this. Let's do incidence rate. Let's go. Please, Dr. Ibrahim, please launch the poll. And I hope my voice is fine now. Dr. Let's look at this name. Dr. Augustine, please let me know if you can hear me fine. Okay, I'm looking through, and we have Louisa Castle. Please get ready to come to the mic. Also, we have a Adeniji, but let's have the, I believe Louisa is a lady, so let's do ladies first.
Sorry, I'm going to end the poll early. I'm sorry that interrupting you. So basically what I noted in the poll is that the Zoom poll asks about cumulative incidence, essentially the last question that we looked at, while the poll on the slide asks about incidence rate. It's the same options, but some people might have that confusing, and so I'm just going to end the poll and then let's just discuss it and move forward.
Okay.
Yeah.
Okay. So so you're saying that it's the same question as poll 8, yes?
Yeah, except in the Zoom poll is the same question as poll 8, but it should be this one that asks about the incidence rate.
I see. So you see that the admonition applies. You have to read the effing question. So me and Ibrahim did not read the question. So all of us are sinners, right? And that's why we have to help each other. So here, what is the incidence rate? So let me bring Louisa to the stage. Please, can you tell us what the answer is and why, or what your answer is and why?
Yes. For me, hello, this is Louisa.
Hi, Louisa.
How are you?
I'm good.
Yeah. For me, I think it's the incident rate supposed to be 30.
Mm-hmm.
Yes, but I'm having a little confusion, which is 30%. That would be B.
That would be B. Okay, so you choose B and tell us why.
Okay. I choose B because that's the only option there, but I have it could be because my confusion is I don't think we should deduct, if I'm calculating, we shouldn't subtract from the population because the population here is 1,000. I think it should remain constant, but I'm seeing 988. So that's my confusion here.
Okay.
Even though I chose B, but I have this confusion.
Okay, I'm going to explain that. Let's bring Adeniji Lasisi Adewale to tell us his answer as well, and then and why, and then we can explain. And I'm going to open this to volunteers, right? To the ghost moders on the group as well. After, there's Annie's, but let's open it to someone who has not asked the question. Just step forward after Adeniji. Adeniji, over to you.
Okay, thank you, sir.
Yes, sir.
With the little understanding I have based on what you have said so far, my answer is A. That is 30 per 980 person years. Since you said that incident basically talking about year, that is the time the person spent throughout the so. That's why I went for that.
And so why 30? Why not 20 per person years?
Okay, I went for 30 per person per 980 person simply because you said what was the incident rate of cancers in 2020?
Right.
In 2020, I think that since and according to this. Oh, wow. It's so well.
Okay, it's okay. It's okay. Thank you. You got the answer. So I'm going to explain the why, so that if you're in another situation, you would know the why. Do we have one more person to volunteer?
I think
someone?
Agnes raised her hand.
Agnes. Okay, let's do Agnes. There's Iya Idako. Get ready. You come up when we're asking questions. All right, Agnes. Oh, I remember Agnes from yesterday. Let's go. Talk to me.
Good evening,
Hi.
Doctor. Okay, I chose A, option A, 30 per 980 person years.
Okay.
Because like you said earlier, incidence rate has to do with time.
Okay.
So the incidence, which is number of new cases, is 30. Yeah, it's for 2020 is 30 per 980 years. We're assuming that 20 people already have cancer, just as you earlier stated, and are no longer at risk of developing cancer.
Yes.
So 30 per 980 person years was my answer.
Excellent, excellent. So we see that the three people have got the different concepts and improved on each other's argument. So to Louisa, the reason why the reason why the answer is A is that the incidence rate, a rate always has to do with time. And you must know the time that we're talking about. The time here is the amount of time the people at risk contribute to the study. So it was, and why it's not 1,000, because you say that's where you got, you're wondering. The reason why it's not 1,000 is exactly what Agnes and Lasisi said, is that 20 people already had the disease, and so they were no longer at risk in 2020. It's the people at risk. The people at risk is 980. If it was a prevalence, it would be the total population. It's the people at risk. I hope that answers the question. Let's move on, except someone has
I think Theophilus has a question.
All right, hit me, Theophilus.
Mary, you sleeping?
Can you mute yourself? I believe Agnes and Louisa. And Theophilus, please ask your question, or mute yourself and ask your question.
I guess we can move on.
Theophilus, we cannot hear you. Is it possible to? Is it possible to type in your answer?
Yeah, I'm already unmuted. Unmute myself.
Okay, ask your question now.
Theophilus, please ask your question. Sorry.
Why don't we move on? I realize that we're now going to be talking about measures of association and effect, and there may be more questions, and we can answer Theophilus's question in the chat. So you can see this picture here. I'm not the one who picked this picture, so please, if you're angry, you should direct it to somebody else. But here, this picture is appropriate because here we are bringing out the big guns, right? But it is not really as big as you think it is, because remember the icebreaker. If you have 20 pounds and another person has 10 pounds, there are only two ways you can compare those people. You can say person one is 10 pounds richer than the other, which is 20 minus 10, or person one is 2 times richer than the other, which is 20 divided by 10. Somebody with a smart mouth will say, well, you can say person one is half as rich as the other person, which is 10 divided by 20. That's fine. It's still a division. Can we mute Theophilus? Theophilus, please ask your question in the chat. We've moved on we're moving to a new topic, and so I'll be happy to answer the question, but please ask it in the chat. Thank you. Okay. Now, so I cite because this is really the big guns. Okay, you can see here there's something called a 2x2. It's a very, very funny name because it's really a 4x4. The 2x2 means 2 rows and 2 columns. So this is 2 rows, column this row 1, row 2, 2 columns, column 1, column 2. But you can see that this entire table is not just 2 by 2, it's really a 4 by 4. And so this it's really funny. Another thing about the 2 by 2 table is that you almost never see it in real life. There's Dr. Fauci is never going to come up and say, according to this 2 by 2, but it is a very, very, very important tool for understanding associations. Okay, now that said, remember what I said in the icebreaker. You can only divide or subtract. You can only divide and subtract. Say it the third time so that you understand it's not difficult. You can only divide and subtract. Now, in public health research, when you divide, it's called a ratio. When you subtract, it's called a difference. When you divide, it's called a ratio. When you divide, it's called a difference. Okay, remember, when it's called a rate, it's time. When you divide, it's called a ratio. They are not the same thing. So if someone says it is a rate ratio, it means you are dividing two things that have to do with time by each other. When you say it is a risk difference or a rate difference, if there's anything like that, it just means you're subtracting something that has to do with time from another thing that has to do with time. Remember, there are only two things you can do: divide a ratio, subtract a difference. Okay, so let's go back to stuff we've been learning earlier. When we look at the odds, of somebody scoring a hat trick, and we look at the odds of another person scoring a hat trick, the odds of Ronaldo scoring a hat trick and the odds of Messi scoring a hat trick, if we subtract those odds, if there's anything like that, it becomes an odds difference. If we divide them, it becomes an odds ratio. When we look at the risk of a child in Anambra State of Nigeria developing typhoid fever, and then we look at the risk of another child in Freetown, Sierra Leone developing typhoid fever, if we subtract that risk, it's a risk difference. If we divide those two risks, it's a relative risk. It's a relative risk, or it is a risk ratio. Again and again and again, only two things you can do: divide, ratio, subtract, difference. Okay, so now let's move, and we're going to select Joshua. So Joshua, get ready. And Joshua and Ernest. Okay, so so remember that this 2 by 2 is really a 4 by 4, and I encourage you, make it a 4 by 4 and it becomes easier for you. Okay, so let us jump straight to understanding what a 2 by 2 does, because it's going to help us. And so Joshua, if you can unmute your mic, tell us what is the risk of the outcome. And an outcome is a disease or something you're looking for to happen, right? The risk of the outcome in the exposed using this 2 by 2. Oops. Joshua there? You have to unmute yourself if you're talking. Yes. Yeah, okay. Let's go. Tell us.
So that's the outcome.
It's the disease.
Is the disease.
Mm-hmm.
That would be. So I don't understand the question.
Okay, so it's okay. It's me.
Yeah.
So look at this statement here. What is the risk or the likelihood of the outcome in the exposed? So what is the exposed? Can you tell me what the exposed is using this 2 by 2 table?
That's A. Like, is that this? Am I supposed
A
to read
plus B? Because
A plus B?
everybody here is exposed, right? You look across the row, right? So it's complicated the first time. So I'm just I have you here for interaction purpose, not because I expect you or everybody to know the answer. This kicks butt all the time. Okay, so just follow me here. Okay, so if the exposed is A plus B, what is the unexposed?
That'll be C over D.
C plus D, right? Because this is unexposed. So let's have an example. Don't worry, we'll keep doing it and everyone will get it, right? So let's say the exposure is mosquito bite. The outcome is the disease. What would be, if it's a mosquito bite in sub-Saharan Africa, what is the outcome, Joshua?
The outcome is...
If a mosquito bites you, what do you get?
Malaria.
There you go. So the outcome of the exposure is a mosquito bite. The outcome is malaria. So remember, this is not academic. You are thinking about it in real life. What is the risk of getting malaria if a mosquito bites you? So if you are exposed, you are A plus B. If a mosquito does not bite you, you are C. Oops. It might be a bad example because a mosquito bite is necessary for you to get malaria. But let's just flow with the example, right? So it's mosquito bite and malaria. So if you are unexposed, you are C plus D. So we have so thank you very much, Joshua. Let's move. I think I called somebody else. Ernest, so we're going to have Ernest doing this interaction, and Nuhu, get ready as well. So if you can unmute yourself, Ernest, then we'll go to Nuhu. Okay, so who died? Ernest?
Sorry,
Yes,
I
Ernest.
accidentally muted you again, Ernest. Can you unmute yourself now?
Okay, Chief Ernest. So let's move to the second one. I see some people answering the first question. So what is the likelihood of the outcome in the unexposed? Ernest, can you walk us through?
The likelihood of the outcome in the unexposed.
Okay, so walk us through by telling us who the unexposed is, what the outcome is, and how you arrive at your answer. Let's go.
Okay, the unexposed are the population that were not exposed to the mosquito bite.
Okay, and on this 2 by 2, it is with who?
C plus D.
Nice. Okay, so and what is the outcome in this group?
The outcome in the group is that they will not have malaria.
The outcome is malaria.
The outcome is malaria. Okay.
Yes. Yes, so I said it's a bad example because if mosquito does not bite you, there's no way you can get malaria, but let's flow with this, right? The outcome is malaria. So what is the likelihood? What is the number of people who get the outcome in the unexposed?
That would be 0.
No, okay, let's not use malaria. It's a bad example. Let's use cancer and smoking. So people who smoke get cancer, but we know that you don't have to not smoke to not get cancer, right? Yes. So what is the unexposed are people who don't smoke. So we got that as C plus D. But what is the number of people who will get cancer even though they are not exposed?
That would be... I don't know. A little bit confused.
Are you looking at my screen?
Yes, I'm looking at your screen.
I'm giving you a hint.
That would be C.
There you go. That would be C. Okay, thank you very much. Okay, let's get Basira on the line. You know, I'm trying to make sure that we understand this and then we'll all move on together. That's the way that we should move. Thank you so much, Ernest. Basira, let's do this. So Basira, so forget the malaria, and I knew it was a bad example because we're going to have that thing. If you don't get bitten by a mosquito, you can't get malaria. So let's use cancer and smoking. If you smoke, you are likely to get cancer. If you don't smoke, you're still likely to get cancer. Okay, so Basira, are you unmuted? Let's go.
Yes, I am.
Okay. So suppose we are trying to research the effect of smoking on lung cancer. What is the exposure? Do you know?
Hello, can you hear me, please?
I can hear you. What is the exposure if we are... Okay, yeah.
The exposure would be the smoking.
Exposure will be smoking. Okay, and so who are the exposed?
The smokers and
the smokers. And who will be the unexposed?
Those smoking and non-smoking.
No, exposed is smokers, right? Smoking is the exposure we are investigating. So I'm playing with words here, but you need to understand this for everybody. You need to understand this to understand where we are going with this. We are researching the effects of smoking on lung cancer. The exposure is smoking. Who are the exposed? It's the people who smoke, smokers.
Okay, yeah.
And who are the unexposed?
Non-smokers.
There you go. So what is the outcome?
It would be smokers plus non-smokers.
What is the outcome?
Cancer.
Lung cancer. Good. Who are the people who have what is the outcome positive? I know I'm changing things up, but I need you to follow me.
Cancer plus
No, we're not looking at the table. Outcome positive is people with cancer. What is outcome negative?
Not coming down with cancer.
Exactly, no cancer. Okay, thank you very much. Let's do one more person. I'm cognizant of time. Let's do one more person. We're going to do this again and again and again and again and again and again. Look at this. I say this is the most useful public health resource ever. Because if you're not able to put things in a 2x2 table in your head, you have no idea what is going on. You will have no idea what is going on. Okay, let's pick somebody else. So I think Amino was the facilitator for yesterday's class. So you are you're an expert, so I'm not going to call you. Sorry about that. Can we have someone? Oh, who's VPAM? VPAM is a smart person and said you can also get malaria from blood transfusion and needle sticks. Absolutely. But you see that a lot of people don't consider that, so it didn't make for a really good example. So VPAM, can you unmute yourself? We have like 1 minute to get this and get everyone's head around this concept, and then we move forward. VPAM, you there? Shall we move to someone else?
Okay.
Agnes, how about you? I know you spoke earlier, or does someone want to volunteer? Raise your hand.
For the number of exposed.
Oh, hold on. I see you're ready. We're ready too. Let's go. So we're talking about exercise.
Okay.
Exercise and obesity, right? Okay, so we're looking at what is the impact of exercise on obesity. So Agnes, what is the exposure?
Exposure.
Yes.
Exercise on obesity. Exposure is no exercise. Is that right?
It could be.
I'm not getting it.
So we are looking at what is the impact of exercising on obesity. In this case, what is our exposure?
Exercise.
Good. And who are the exposed?
People who exercise.
Excellent. And who are the unexposed?
People who do not exercise.
Exactly. And what is the outcome?
Obesity.
And who are the outcome positive people?
People who are obese.
And who are the outcome negative people?
People who exercise who are not obese.
Outcome negative is people who are not obese.
Okay, the non-obese.
Exactly. Exactly. So you're on genius mode. Let's keep going. Now let's come to this 2x2 table. Or let's do one more example. Okay. I'm cognizant of time, but we really need to establish this before you move forward. Otherwise, we're wasting our time. Let us look at the impact of reading to your children on future socioeconomic performance. What is the exposure?
Reading
to your children, not just reading.
Reading to your children.
Right.
Reading
Okay. I need you to keep giving us back to back. That's the exposure. Who are the exposed?
The children who are read to.
Excellent. Who are the unexposed?
The children who aren't read to.
What is the outcome?
Does the way you put it?
Socioeconomic performance, future socioeconomic performance.
Okay, so that should be like improved socioeconomic performance.
So that's the outcome positive, right?
Yeah.
Okay, and what is outcome negative?
A decline in positive socioeconomic performance.
Exactly. And you can define this so we're going to stop here and move on because we've done this example over time, right? Now let us go to why this is important. Forget about this slide. Absolutely take it out of your mind. Take this one out of your mind. Oh my God. Let's see. Let's come back here. Okay, let's use this because if people are not getting this as much, then those formulas are going to be crazy. Okay, let's continue to work with Agnes. Agnes, give us some more of your time, okay? Except someone raises their hand. I see a Busui and Olua Busayomi. Let's do this. Okay, so Agnes, let's go. Genius mode. Now, what is the risk of, suppose we're talking about smoking and lung cancer. We're back to smoking and lung cancer. What is the risk of having the outcome if you are exposed? Looking at the 2x2 table or the 4x4, whatever we're going to call it.
Okay, the risk of having the outcome if you're exposed should be, do we say A over A plus B?
Exactly. Excellent. Let's go. What is the risk in the second group? What is the second group?
The unexposed group.
The unexposed group. Okay, so yeah, and what is the risk of the outcome in the unexposed? Some people are raising their hands. Ibrahim, you're going to help us after Agnes does her 87 matches unbeaten. Let's go.
Okay, that should be C over C plus D.
Excellent. Okay, thank you very much. Ibrahim, please give us a name from people raising up their hands.
Abbas.
Abbas, unmute yourself. Let's do this. So now let's move into, remember, we started by saying a ratio is a division, a difference is a subtraction. Okay? Yes. Okay, great. So therefore, Abbas, what is the risk ratio of smoking or smokers versus non-smokers in getting lung cancer?
The risk ratio of smokers versus getting cancer. That would be yeah.
I'm going to do something. No, can you all see my screen?
Yes, I can see it.
You can see my screen still?
Yes, okay, I can see it.
I'm going to do something very quickly, and then you help me here.
Okay.
So you can still see my, yes, which of my screens can you see?
I can see, yeah, okay. Now you are exiting full screen.
Yeah, so you had a full screen with, okay.
Are we back?
Yes.
Okay, so instead of saying A divided by A plus B, we know A plus B is equals to X. Okay, so tell me, what is the risk, relative risk of smokers versus non-smokers in the development of lung cancer?
Smokers versus non-smokers in the, that will be exposed to the cancer. That will be A over X minus Y.
A over X is the remember that a risk ratio. Did I say difference?
Sorry, risk ratio.
Okay.
You said ratio, yeah.
Okay, go. Let's do it again. Can we add a whiteboard demonstration? Oh, good idea. Okay, I'll do that after Abbas gives us his own genius mode. So the risk in the exposed smokers is A over X.
Yes.
The risk in the unexposed is C over Y.
Yes.
So the risk ratio is going to be A over X divided by
Y.
C over Y, not Y, divided by, is the risk in the exposed divided by the risk in the unexposed.
Okay, yes.
Okay, and so I want to shout out some people. Tolu Amusa is giving us the answers. Maxwell is giving us answers. Lukman Jibril, nice, thank you so much. Nuhu is giving us good answers as well. Nuhu, make sure you get your board mass correctly. I see your answer. I know where you're going, but the mathematical may not be so great. So do we want to take one more person?
Yeah.
Then we can go to okay, good. Who else is raising their hands? Hi. Okay, so who's this? Who's the person speaking?
Tammy.
Oh, hi Tammy, how are you? Okay, Tammy, let's go. So give us the risk difference. So Abbas gave us genius mode, he gave us the risk ratio. Give us the risk difference.
So the risk difference would be A over X minus C over Y.
Oh my God. Okay, genius, 1,000 points. Let's go. Let's keep going. Now, give us the odds ratio.
The odds ratio will be, I'm calling it AD divided by CB.
Okay, that's cheat mode. That's cheat mode. Come on, that's cheat mode. Okay, so tell us what. Can you tell us why?
Why?
Yes.
That's the formula for odds ratio.
Okay, remember that the odds is the likelihood of a thing happening. Okay, let's use a whiteboard. Let's do whiteboard. Egbon, how do I do whiteboard? Okay, I think I see it. Does anyone see my whiteboard? New share.
Yes, we do.
Okay, let's go. I'm going to use my fingers here. And You see my whiteboard? Okay, let me draw a 2 by 2 real quick. Come on, whiteboard. It's my whiteboard. Why is it not working? I need help here. I cannot whiteboard on the whiteboard. Can you see it? Oh, Zoom.
I think let's just move on, and
Okay.
we can figure this out after.
Okay,
Yeah.
let's do that. So yeah, it's whiteboard's not, it's not whiteboarding. So let me see where we are. 45. Okay, so we'll move to the polls soon. I want to try to explain how to get the odds ratios in 4 minutes. Okay, so I have to go into genius mode now. So remember that an odds is the likelihood of a thing happening divided by the likelihood of it not happening. So the likelihood of a person who smokes getting cancer is A divided by A over B. And let me know if you follow me, because this is the likelihood of it of you getting the disease if you're a smoker, is A divided by X divided by the odds of it not happening, which is B divided by X. So remember when we said 75% of people got the answer right. So it was 75% divided by 25%. It's really 75 over 100 divided by 25 over 100. So it's A divided by X divided by B divided by X. And what you have when you cancel out, remember that in division you flip, it becomes A over B. So the odds of the disease in the exposed is A over B. The odds of the disease in the unexposed is C divided by Y divided by D divided by Y, which is C divided by D. So the odds in the exposed is A over B. The odds in the unexposed is C over D. When you divide those two, in division, you flip it. Remember that you flip it. So C over D becomes D over C, and your division becomes multiplication. And that's why Temi said the answer is A times D divided by B times C. That is your odds ratio. That's how you get your odds ratio. So if the math is not mathing, just always do A times D divided by B times C. Okay, so we're going to stop here because of time and move on to interpretation, but we're going to take polls, and we're going to stay behind to answer questions after the session ends, so feel free to come in. Okay, so now I'm going to pretend like all of us understand this 2 by 2. It's a magical table. Feel free to practice. Okay, we're not going to do this. We're not going to do this. But we're going to do this, right? Because they are interpretations. Now, interpretations real quick. If your RR or your OR or your HR is hazard ratio, they're really the same, kind of the same thing, is greater than 1, but it is less than 2. For example, 1.4. What you're going to do is you're going to subtract 1 from 1.4. Follow this, right? Because it flips in another situation. And what you get is 0.4. You make that a percentage, that is, you multiply it by 100%, it becomes 40%. And your answer would be 40% more likely. Again, if it is greater than 1 but less than 2, you take that value, you subtract 1 from it, you make it a percentage, and then your interpretation becomes 40% or X% more likely, emphasis on the more likely. So if we're looking at smoking, the effect of smoking on lung cancer, your interpretation, if you had a risk ratio of 1.4, would be that smokers are 40% more likely to get lung cancer than non-smokers. That is how to make it make sense. Remember, public health is for decision making. You say, Mr. Governor, we need to address smoking in Sierra Leone, in Freetown. Why? Because smokers are 40% more likely to get lung cancer than people who don't smoke. And the government is going to be, wow, here's money, go start a program. If this value, however, is less than 1, when it's less than 1, is usually protective, but we won't get into that. What you do is, whereas above you subtract 1 from that value, you subtract this value from 1. If it's less than 1, subtract from 1, because you can never, or you should never, get a negative RR, HR, or OR. There's no such thing. And so if, for example, it was 0.83, when you subtract from 1, it becomes 0.17. When you multiply by 100%, it becomes 17%. And then you go to Mr. Governor and you say, Mr. Governor, people who exercise are 17% less likely to become obese than people who do not exercise. And the governor is going to say, here's your money. Take and go and create parks where people can gym and exercise, and beautify this place with parks where people can exercise. Excellent. And the third way to interpret data, when your RR, OR, or whatever R is greater or equal to 2, don't do anything. Don't do anything. Just go to the governor and say, people who smoke are 2.3 times more likely to get cancer than people who do not smoke. And the governor will say, yeah, I think we need to ban smoking in Liberia, Sierra Leone, Tanzania, Nigeria, and we have to kick out all the people manufacturing cigarettes from Africa. This is what public health is about. You take a concept, you identify exposed and unexposed, you either divide or subtract, and you interpret your results. It is not academic. See, Ronaldo has scored twice as many goals as Messi. He is 2 times better than Messi, or whatever you people agree on Twitter. Okay, let's do polls. Let's do polls quickly. Then in the last 10 minutes, we'll jump to things that can affect your study results. Dr. Ibrahim, over to you. Oops. Okay. Okay, maybe we can close the poll. No, this takes a while. Let's give it 1 more minute and then close the polls.
Okay, closing the poll now.
Okay, let's do that. Okay, so what is our answer? 45 people chose 0.4, but the answer is 0.25. So let me walk us through. Tolu Lokwe Musa, let's have you unmuted. Let's help me. Let's do this together. So remember that your risk ratio is the risk in the exposed divided by the risk in the unexposed. Tolu, hit me quickly. Who's the exposed in this case?
The exposed are those that
You have to talk quickly, my good man.
Okay, so can you hear me, please?
Yeah, hit me quickly.
Yeah, so the exposed are those that have that took iron supplements.
Okay, so it's people who took iron supplements, and the unexposed are people who did not take the iron supplements.
Yeah,
and so what is the let's call it the risk? Yes, it's the risk of anemia in the exposed.
That's 10 over 100.
That's 0.1. And what is the risk in the unexposed?
That's 50 over 200.
Okay, and so when you, and remember that the risk ratio is you divide exposed, risk in exposed over risk in unexposed. So that is 0.1 divided by 0.25, it gives you 0.4. Tolu, genius mode, hit me very quickly. What is the interpretation of this result?
Okay, so this means that those that took,
No, go. It's 0.4, man.
Yes. So it means that those that took iron supplements are 40% less likely to come down with anemia than those that
I confused you, right? Because I didn't give you enough time. Remember that when it is less than 1, you subtract from 1. So they are 60% less likely. Great. Let's launch the second poll, and then we'll quickly move and see. Thank you, Lukman, Jibril. Let's launch the second poll. Let's go. Okay, so let's go. I really want to talk about confounding. It's one of the, it's another mind tickle, and it's really good because you can use it in your personal lives as well as in your research, and you need to know about it. But let's see what I can do in,
you can skip some of the polls if
let's do like 2 more. Because yes, it's better if you understand some stuff than if you are introduced to stuff without understanding it. So while we're doing this poll, Temi is saying, can we interpret, do the interpretation again? If your value is greater than 1, example 1.4, you subtract 1 from it. It becomes 0.4. You make that a percentage, it becomes 40%. Your interpretation becomes 40% more likely. If it is less than 1, you subtract it from 1. So if it was 0.4, you say 1 minus 0.4, it becomes 0.6, and you say 60% less likely. That's the interpretation. Okay, we've closed this poll. So what is the risk difference? So let's have Lukman help us with this. So the risk difference, negative 0.15, 65% of people got this. Wow, this is really, really good. And so let's move to the next poll, and then Lukman can help us with that. So Abode Emilomo says it should be 80%. The answer was 0.4. So it's 1 minus 0.4. Let's launch the next poll. Since a lot of people got this, let's see if, this is the next poll. Okay, yeah, let's do this. Let's just flow with what's going on. I can explain while it's 0.5 or negative 0.5 while we're going, or look at the explanation here so that I can be a little quiet. It's the risk in the exposed minus the risk in the unexposed. And so you have 10 divided by 100, because we said the exposed are the people who took the supplements. 10 divided by 100 minus 50 divided by 100. And that is why you have 0. And you see that a difference can be negative. That means there is a protective benefit. So if it's positive, it is a risk. If it is negative, it means it's beneficial. So when you go to the governor, you're going to say, Mr. Governor, we are going to have 0.15 less incidence. I'm not going to go into the description of that. Less incidence than people if you don't give these girls iron supplements of anemia. And you say, here's money, go buy, give everybody iron. Girl, boy, man, woman, just give everybody iron. Okay, so let's close pole 12, and then I would jump to I will jump real quick to what's the other thing? Okay, a case control. Okay, so this is the reason why we need this is for case controls, you mostly only, not always, but mostly only can calculate an odds ratio. That is why. And the reason why is temporality, and Dr. Moshood explained that last week. Okay, let's move to confounding. Let's do it in 5 minutes. Okay, so confounding, like I told you, it's really, really interesting. I really like it because, and it's this excellent example. It's a real life story, right? Before it became fashionable to drink coffee, now there's a coffee house everywhere. Before it became fashionable to drink coffee, researchers thought that drinking coffee could cause bladder cancer because they were seeing a lot of bladder cancer. And when they were talking to these patients, the patients were like, oh, I drink a lot of coffee. So they did this study, they spent so much money, and they found out that, oh my God, people who drink more than 2 cups of coffee tend to get bladder cancer. So if we had time, I would have said, what's the exposure? What's the outcome? So the exposure is drinking coffee, more than 2 cups of coffee. The outcome is bladder cancer. The exposed are people who drink more than 2 cups. The unexposed are people who drink less than 2 cups. However, after they published their results, somebody, let's call that person Emilomo Michelle Oluwabusayomi, told them and said, hey, have you guys considered that people who tend to drink a lot of coffee also tend to smoke a lot? Because people who drink coffee before it became popular to drink coffee were anxious people who had anxiety, who were always on edge. Those people smoked a lot. And so it may not be the coffee that is causing the bladder cancer as much as it is the fact that those people also smoke a lot. And that is a perfect example of confounding. When you are doing studies, research, for example, mothers who read to their babies end up being richer than mothers who didn't read to children whose mothers, blah, blah, blah. You might say it's true. But however, have you ever thought that people whose mothers can afford to read to them are already rich in the first place, and the children of wealthy people tend to become wealthy as well? So before you go out saying studies have shown this, you need to think about confounding. Now, there are 3 things that you need to look at to really determine that something is a confounder. The one is that 2 of them, the 2 exposures, are associated, meaning if you see that the people who drink a lot of coffee also tend to smoke a lot, that means they are associated. If they had nothing to do with each other, it cannot be a confounder. At the same time, the 2 exposures need to be related to the outcome. Maybe in this case, in my example, is a little bad because it's a real life example. Drinking coffee, I don't think it causes bladder cancer, right? So it's a bad example. But let's imagine that drinking coffee causes small bladder cancer and smoking also causes bladder cancer. 2 of them also have to cause the outcome. Otherwise, they are not confounding each other. And lastly, they should not be in the causal pathway. To be in the causal pathway means one thing happens, then the other happens, then the other happens. For example, hypertension leads to stroke. Stroke leads to death. Stroke is in the causal pathway of how hypertension can lead to death. So those 2 things must not be in each other's causal pathway. And that is how you explain or how you look out for confounding. So when you're discussing papers, be on the lookout for confounders. Exercise leads to, exercise leads to obesity, right? However, exercise leads to a reduction in obesity. However, the people who like to exercise also like to eat healthy. They like to eat healthy. So eating healthy may be confounding that relationship between exercising and a reduction in weight. We have 1 more minute to go. So I'm going to skip this because of time. I wanted to make sure there's effect modification. We can do that next time if you want. It's really important, but not as important as confounding. What I really wanted you people to understand is how to understand the measures of association, which is what this session was about. And we've gone over that and we spent some time doing that. And I think that that's what is really, really useful for you, because that's what you need to convince people when you are making decisions. So at this point, I will pause, except you have questions, or except Ibrahim has something to say. And